Good afternoon, dear participants and dear organizer of the Conference of Climate Science Agriculture for Asia 18th TSAE International Conference. Um, in the in the part, I'm going to talk about modeling and evaluation of heat transfer enhancement in PCM-based energy storage system. As you know, the classification of the thermal energy storage system into divided into four parts: latent heat energy storage system, sensible heat storage system, thermochemical heat storage system, and we have also hybrid heat storage system. And you know, all types of thermal energy storage system has unique advantages and disadvantages. First, for example, in order to store 6.7 gigajoule energy in sensible heat storage system, we should have a 34 cubic meter. However, in the latent heat storage system, in order to store this energy in latent heat energy storage system, we should have a 20 cubic meter. But in to store this energy in thermochemical heat storage system, we need 1 cubic meter. It can be analyzed that the thermochemical heat storage system requiring the less storage volume compared to the other types of thermal energy storage system, but the expense for construction of the thermochemical heat storage system require much costs compared to the other storage system. And the operation of the thermochemical heat storage system is also very complex compared to the sensible and latent one. And that's why we are in our study we are focusing on the latent heat energy storage system. And you know, the latent heat energy storage system, the storage medium can be solid to the solid, solid to the liquid, liquid to the gas. And you can see the classification of fast transition mechanism of the figure 3. And we are just built the latent heat energy storage system with a finite structure in 2D model of the conventional multiphysics. And you can see the 2D geometric view of the latent heat energy storage design. And boundary condition, thermophysical properties of the material, mesh characteristics for the numerical model are demonstrated in the table 1, table 2, and table 3. And we have used finite element method to solve the three-dimensional Navier-Stokes equation with the energy equation. And water is used as a heat transfer fluid in our system. PCM at the 60 was selected as a storage medium, and the container of the storage latent heat storage system is made of aluminum. Inlet velocity of the fluid is about 2 liter over minute. Initial temperature 25 degrees C. Inlet temperature of the heat transfer fluid 80 degrees C. And all equation in that page of the presentation are inserted to the variable part of the conventional multiphysics to analyze the temperature variation, total storage energy, melting fraction, something like that. In the next page of the presentation, we can see the temperature variation, surface temperature variation of the two latent heat energy storage system during 20 12 hours during 12 hours, and also melting fraction of the latent heat energy storage one is also demonstrated. You can see, and in the next page of the presentation, in the next page of the presentation, we can see the melting fraction of the two latent heat energy storage system. In the first graph, the melting fraction of the latent heat energy storage one. In the second graph, the melting fraction of the latent heat energy storage two. Both of them have the finite structure, but you know, the all part of the PCM has transferred into the solid, into the liquid in latent heat energy storage too. I mean, the much part of the PCM has transferred to the liquid during that hours. I mean that this latent heat energy storage too showing the better performance compared to the first one. Let's turn to the discussion. Just in this part, we can see the temperature variation of two different latent heat energy storage system at 3 different points. Stored energy of the system has also demonstrated. Latent heat energy storage, the temperature variation of the latent heat energy storage one is demonstrated in the figure 6 and figure 6a, and latent heat energy storage 2, the temperature variation of the latent heat energy storage 2 is demonstrated in the figure 6b. As you can see, the stored energy of the latent heat energy storage system, latent heat energy storage system 2 is a bit higher compared to the first one, and temperature also temperature variation at 3 different points are also a bit higher compared to the first one. I mean that the change in the finite structure of the latent heat energy storage system enhancing the thermal performance, just melting time of the PCM. That's why second one is showing the better performance compared to the first one. Let's turn to the conclusion. This study has demonstrated the thermal performance of the latent heat energy storage system can be significantly enhanced through strategic fin integration and design optimization. By comparing to finite configuration over 12 hours charging period using numerical simulation, it was observed that the optimized latent heat energy storage design to facilitate faster and more uniform melting fraction of the fast change material, resulting in higher and more consistent temperature distribution across the storage domain. Temperature and melting fraction analysis clearly revealed that the latent heat energy storage 2 achieved more effective thermal penetration, especially at deeper location with the PCM. However, stored energy evaluation at multiple points showed that latent heat energy storage 2 stored a great amount of thermal energy in shorter period, with reduced thermal lag compared to the latent heat energy storage 1. This finding confirms that the internal fin geometry plays a crucial role in overcoming low thermal conductivity limitation of the PCM. The result of our practical guidance for the development of more efficient and compact thermal energy storage solution, particularly relevant for the renewable energy system requiring rapid and reliable heat exchange. That's all. Thanks for your attention.